Recording. This one, is this what we want? Yeah, it's 4 now. That's 4.3. Extreme values of functions. Definition: absolute extreme values. Let f be a function with domain D, then f of c is the absolute max value of D if and only if everything else is less than the point we're looking at. If everything else is less than what we're looking at, that must be the absolute maximum value. It's the absolute minimum value on D if and only if everything else is greater than the point we're looking at. So if everything is greater than, then that's the absolute minimum value. So I think it kind of states the obvious in a very complicated way. If all your points are above this point, you've found the absolute minimum. Absolute or global maximum minimum values are also called absolute extrema. We often omit the term absolute or global and just say maximum or minimum. So if you see the word maximum, that means absolute maximum. If you see local minimum, then it's the local minimum and not the absolute one. So if we omit the word local, we mean, or omit the word global. If you just see max or min, we mean the overall one. Example 1, exploring extreme values. Here we have the cosine of x on just negative pi over 2 to pi over 2. On this interval, we have a maximum of 1 at x equals 0. Thank you. And the AP wants you to write it like that. So the way I wrote it is very important. Maximum of blank at x equals blank. So the actual maximum value is the y value, it's 1. And then it's happening when x is equal to 0. If you write it in a different way, you may or may not get full credit. I know if you write it like that, you'll get full credit for it. We have a minimum of 0 at x equals plus or minus pi over 2, and we can see on the interval including the values. So you can have multiple places where you get the maximum value. You can have multiple places where you get the minimum value, no problem. Now for sine, I think the other one's sine, yes. We have a minimum of negative 1 at x equals negative pi over 2. That's this one over there on this interval. And we have a maximum of 1 at x equals pi over 2. So the minimums and maximums are happening on the endpoints. On cosine, we had a maximum happen in the middle. Exploring absolute extrema. What about open and closed dots? That's what we're talking about here. Now, overall, if you go from negative infinity to infinity, there's only an absolute minimum only. If you limit the domain from 0 to 2, but include them, 0 and 2, then we have an overall maximum at this point, and we have an overall minimum at that endpoint. Here we can see don't include 0, but include 2. So in other words, open dot at 0, closed dot at 2. So we only have a maximum. We do not have a minimum because you can decrease to that open dot forever. You can get closer and closer and closer. So there's never a lowest value. It can always go lower. So this only has a maximum. Now if you don't include either one of them, then you have no absolute maximum or minimum. There's neither. We don't have a maximum value there. We don't have a minimum value there because you can always get closer to both of those open dots. Local versus or relative versus global. Here we have the absolute minimum on the endpoint. Here we have a local maximum. And we have a local maximum. Well, interestingly enough, the slope of the tangent line at a min or a max is 0. That becomes a huge deal. We have a local minimum here, and the slope of the tangent line is also 0. Here we have the global maximum, but the first derivative is undefined there. So we care where first derivatives are 0. We care where they're undefined. and then we just have a local minimum over here at that endpoint. Let C be an interior point in the domain of the function, so not at an endpoint. Then f of C is a local maximum value at C if and only if everybody else surrounding it is smaller than that value. So if everything surrounding is smaller, you have a local maximum. So it's very similar to that other definition. You have a local minimum value if everything surrounding it is greater. So if you have a point and everything surrounding it is greater than, has a y value that's greater, you have a local minimum. Seems intuitive, but now it's official, in other words. There we go. Finding extreme values. Interior domain point where the function has local extreme values are points where either f prime is 0 or f prime does not exist. So right here at these local mins and maxes, the slope is 0. Here's a global max. That's where the first derivative does not exist. If a function f has a local maximum value or local minimum value at the interior point C of its domain, and if f prime exists at C, then f prime of C is equal to 0. We care about zeros. We care a lot about zeros. And here's just a vocabulary word, a critical point. Where f prime is 0 or undefined, we call that a critical point, which means it's a potential minimum or maximum, only potential. Doesn't have to be. Find the absolute max and min values of that function on the interval -2 to 3. Now, our mins and maxes can happen at endpoints, so we'll test the endpoints. We'll check those values. But then we want to check any values in between that could possibly be a minimum or a maximum. So let's do the first derivative. F prime of x is 2/3 x to the -1/3. That's 2 over 3 times the third root of x. Now there's no way to get that first derivative to be 0. There are no variables in the numerator, none. That first derivative can't be 0. But the first derivative is undefined at x equals 0. So a potential min or max can happen at 0. That's where the first derivative is undefined. Well, now we just compare the actual values. So we just plug those values back into the original. So I need -2 to the 2/3. And we're going to have calculator with this, because now we got to really compare decimal values. So -2 to the 2/3. And that's 1.587. If I plug 0 in, that's 0. And let's see, 3 raised to the 2/3. That's 2.080, 2.080. So we have a maximum of 2.080 at x equals 3 and a minimum of 0 at x equals 0. So the minimum happened to be, actually happened where the first derivative was undefined. Now if we look at this graph very quickly, it doesn't ask you to do that, but let's take a look and see if it kind of makes sense, if it actually happened. So if we graph this, zoom 6, we notice that at 0 there is a cusp. But not only is it a cusp, it happens to be the lowest value on this interval, from -2 to 3. So let's investigate that. -2 to 3, that's what we should be looking at here. There's the cusp, it is the lowest value, and that value to the right is a little higher than this one. I know it's actually hard to see that. Find the extreme values of this function. Now this function is a little different in that we want to kind of explore the domain of this one. The domain, well, we can't take the square root of negative values and we can't have the denominator be 0. So we want 4 minus x squared to be greater than 0. It can't even be equal to, because this is in the denominator. But 4 minus x squared, that's an upside down parabola. And so we want from -2 to 2 is the domain, but we can't include -2 and 2 either. So that's the only place where this parabola is positive. And wherever it's negative, we can't include that. So the domain is negative 2 to 2. We can only talk about the derivative where the actual function exists. So we got to keep that in mind when we're doing derivative. So f of x is equal to 4 minus x squared to the negative 1/2. Now I haven't done the derivative yet. We just changed what the function looks like. So f prime of x is equal to negative 1/2, 4 minus x squared to the negative 3/2, but then times negative 2x. And if you're still wondering what the derivative is, if you still can't do the derivative, how are you going to move on in this class? You're going to have to get some help, either from me, or look it up on the internet, or review some notes, or ask a friend, poll the audience, whatever you need to do. That's a Who Wants to Be a Millionaire reference. Negative times a negative is a positive, so x over the square root of 4 minus x squared to the third. So we want to know where the first derivative is 0. That's where the top is 0. X equals 0. And where the first derivative is undefined. But the derivative and the domain of the derivative and the domain of the original function are exactly the same. So on the domain, the derivative isn't undefined anywhere. Now there are places where this is undefined, but that's exactly where the function's not defined. So the only place I care about is x equals 0, in other words. That's what I'm trying to get at. Find the extreme values. So, well, here's how we should end it in this section. Let's look at the graph. We're going to go 1 divided by the square root of 4 minus x squared. And I don't care that, I kind of want you to use your calculator to find this stuff out. So we're going to go zoom 6. But the graph is pretty tiny. So we'll have to zoom in on this. Zoom number 1 is zoom box. Enter. So at 0, we have a local what? Local minimum or local maximum? Minimum, right? We have a minimum. Actually, it's the global minimum as well. So we have a minimum. Let's see, find the extreme values. So it's actually a minimum of, if I plug 0 in, 1 over square root of 4 is 2, so minimum of 1/2. That's the actual answer. It doesn't ask where is it. So you don't have to answer where is it. If you said minimum of 1/2 at x equals 0, I'm not going to count it wrong though, if you give me extra information. But I said in this section, this is how I kind of want you to finish it. Just look at a graph and go, oh yeah, that's a minimum. But I want to give you a sneak peek on what we're going to do later. If I were to have a graph and a function is decreasing, what are all the slopes of a decreasing function? Are those positives or negatives? Negatives. And then if the function increases after that, or increases in general, all of the slopes are positive. So if your slopes go from negative to positive, you have a minimum. If you have an increasing function, the slopes are positive, and then a decreasing, then the slopes are negative. So now if we plug in, what do I have to plug in? I'm going from negative 2 to 2, negative 1 to 1. If I plug negative 1 into the derivative, if I'm square rooting, there's no way to get a negative out of this denominator. So if I plug a negative 1 in, I get a negative. And if I plug a positive 1 into the derivative, I get a positive value, because the denominator in this case has to be positive. So the derivatives are going from negatives to positives, negative to positive. That's a minimum. So that's really what we're going to do later. In this section, I just want you to use your calculators quite a bit and just investigate what's happening at these points. Now I want you to do the derivative by hand so you get practice doing that and find the values. while a function's extrema can occur only at a critical points and endpoints, not every critical point or endpoint signals the presence of an extreme value. What does that say? If your first derivative is equal to 0, that does not mean you have a minimum or maximum. You could have what we call a point of inflection, or you could have a vertical tangent line, neither of which are mins and maxes. When you find where your first derivative is 0, you have potential mins and maxes, not guaranteed. Find extreme values. Find the extreme values of this piecewise function. F prime of x is equal to, what do we got? Negative 4x for x less than 1 and 1 for x greater than 1. There's the derivative. And you might say, well, what about the equal? We can have the equal on the function value because there's actually a point here. But I cannot have the equal to on this because there's no slope there. You can see that the two slopes are different. This tangent line and this tangent line are not the same. So I can't have the equal over there. Find extreme values. Well, I have an absolute, no, not absolute. I have a local max of 0, that's what makes this derivative 0, of 4 at x equals 0. So I made the first derivative 0. But then we also have a local minimum of 3 at x equals 1. And that's where the slope is undefined. So we found out where the slope is 0, that's at 0, and the slope is undefined at 1. That is also an extreme value. Definitely use the calculator on this one. You want to grab your calculators and play along? That's quite the function. Let's get it entered in. Y equals natural log, absolute values in math over at num, absolute value of, did I get the natural log? I did. X divided by 1 plus x squared. And we can go zoom 6. I like the zoom 6. It's all negative 10 to 10s, and then I can adjust it from there. The local maximums, actually the global maximums, are happening really close to 0. So I'm going to zoom in. I like zoom box, number 1, because I can really control it. I can just box it in exactly where I want. I don't have to guess what numbers to use. I can literally box it in. So there's a global max, and then we have a global max on the other side. Now I know enough about natural log to know that down the middle, it looks like that. It's going down to negative infinity. And whenever you take the absolute value of a function, if you take the absolute value of the entire function, it makes all the y values positive. If you take the absolute value of just the variable part, it makes it symmetric over the y-axis. So if we go second, calculate a maximum, and we can go get this one over here. There we go. To the left of the maximum, I got to get over to the right of the maximum, and then it says get me close. Now, it says guess, but it's like, all right, get me close to where you think it is. Now these calculators, when they do all the functions, are accurate to about 6 decimal places. They can't get much more accurate than that. That's why you're seeing negative 0.999998. But that's really negative 1. So find the extreme values. So we have a maximum of negative 0.693 at x equals negative 1. I don't want you to think that the number is actually negative 0.99999. Because of the accuracy of these calculators when we do these kinds of functions. But that happens at plus or minus 1. So that same value is happening over there at plus 1. One other thing I want to show you on this is that if we calculate the derivative number 6 at negative 1, it's 0. But look at that number. It's saying the slope or the derivative is 0.1, 2, 3, 4, 5. It's saying that's the slope. Well, again, the accuracy of these are only to 6 decimal places, so that's actually saying it's 0. And sometimes it will just say 0. I don't know why it does sometimes and sometimes it doesn't. But that's exactly what we would expect the slope of the tangent line to be at that maximum value, is 0. Any questions? There's a few ways to use your calculator. All right, what are we going to see in the homework? Find the extreme values and where they occur. On number 2, we're going up to an open dot and down to an open dot. So none. We don't have a maximum and we don't have a minimum. It will not get to either one. Number 4, we have a maximum. What does it say? Find the extreme values and where they occur. Maximum of 2 at x equals 1. And we have a minimum of negative 1, and that's happening at x equals 0. So if you follow that format, again, I'm going to tell you again, if you follow that format on how to write your answer, I can guarantee you 100% credit on that. If you play your own game or change it up, I don't know, we'll see. Identify each x value at which any absolute extreme value occurs. Explain how your answer is consistent with the extreme value theorem. We don't do that. So we have, all I can say on this one is a maximum at x equals c and a minimum at x equals b. They don't have any y values. All right, now we get into some math. Use the candidates test to find the extreme values of the function on the interval and say where they occur. We don't do stationary points. Don't worry about that. So what are we doing? Finding the extreme values. We need g of negative 1 and we need g of 1. We need the endpoints. We need those values. And since we're doing e, we may or may not have to use our calculator. On this one, I don't think we do, actually. But I need anything in between. G prime of x is negative e to the negative x, which is negative 1 over e to the x. Now there's no way to make that 0. The top is not, doesn't have any variables in it. It's 1, or negative 1 if you want to call it negative 1. But either way, we can't make that 0. And we can't make e to the x 0 either. So this has no critical points on this interval, or anywhere for that matter. So one of these is going to be the biggest value and one of them is going to be the smallest value. So in other words, your minimums and maximums are happening at the endpoints. So this is actually going to be what? E to the negative 1. And then this is e to the negative 1 or 1 over e. So this is like saying this is 3 and this is 1/3. So maximum of e at x equals negative 1 and minimum of 1 over e at x equals 1. So the minimum maximum are happening at the endpoints. There's no twisting or turning. There's no minimums maximums on the middle, on the interior we call it, of that interval. I want you to pay attention to this one. I see how much fun you're having with all this material. A lot of just me presenting stuff today. It's not very interactive, if you will. So are we focused up? Are we ready to go on this one? This one's a rough one, all right? Because it's trig and it makes it a little harder. But I want you to focus up on this. There's a lot of math here. It starts out exact same way. We want f of 0, and I'm just going to put it off to the side now. F of 7 pi over 4. Let's get those values because they're pretty easy actually. Sine of pi over 4 is square root of 2 over 2. And let's see, 7 pi over 4 plus pi, that's 8 pi over 4. Oh, that's 2 pi. That's 0. So we took care of the endpoints. The middle is a little rougher on this one. Takes a little bit more math. First derivative is cosine of x plus pi over 4. Times 1, right? Times the derivative of the inside. But now we want to know where that is 0. Let's just try to, I don't know. Let's try to just think about it, and then I'll show you how to do it by steps. Where is cosine 0? Pi over 2 and 3 pi over 2. We'll go one time around. So what do we add to pi over 4 to get pi over 2? Another pi over 4, isn't it? What do we add? This is a little harder. What do we add to pi over 4 to get 3 pi over 2? 5 pi over 4, right? Because then it'd be 6 pi over 4 and then it'd be 3 pi over 2. But what if it's not? What if it's a little harder than that? What are we going to do? Well, we're going to first take the inverse cosine of both sides. So we're first going to answer where is the inverse cosine, where is cosine 0? That's the first thing I asked you. And so we want x plus pi over 4 equal to pi over 2. And we want x plus pi over 4 to be 3 pi over 2. And that's exactly what we said. We wanted this to be pi over 2 and 3 pi over 2. So now x is 2 pi over 4 minus pi over 4. And this is exactly what we said x should be, pi over 4. X is now equal to 3 pi over 2 minus, 6 pi over 4 minus pi over 4. And we said the other one was 5 pi over 4. That's how to do it in steps. So we have 2 critical points on the interior of our interval. So now I want to plug those back into the original. We want f of pi over 4. And I want f of 5 pi over 4, and I can compare those to the 2 values I have. So there's 4 candidates, 2 of which are going to be the answer. Let's find out which one they are. What does that say? Pi over 4? I can't read my own handwriting. What's sine of pi over 2? 1. 5 pi over 4 plus 1 pi over 4 is 6 pi over 4, negative 1. 3 pi over 2, negative 1. Oh, so these are the 2 winners. If you look at square root of 2 over 2, it's about 0.7. Hello, calculator. Turn on. Thank you. Square root of 2 divided by 2 is about 0.7-ish. There we go. So maximum of 1 at x equals pi over 4 and a minimum of negative 1 at x equals 5 pi over 4. There we go. Now, how do we know? I mean, let's take a look at what's happening here. We have sine of x plus pi divided by 4, right? So there's the function. And we're only going to look at 0 to 7 pi divided by 4. What should we go by? Pi over 4s? Pi divided by 4. And how about negative 2 to 2? So we're saying we get our highest value at pi over 4 and our lowest value at 1, 2, 3, 4, 5 pi over 4 right there. Matches, doesn't it? There's the pi over 4. There's the 5 pi over 4. Here and here. We got it. It all works. Derivative's pretty cool. If it wasn't so much work, you'd think it's cooler. Let's do these 2. I know if you're watching this at home, it doesn't matter, but I want to go over the tests. So 6 period 23. Oh, we got plenty of time. Let's try number 18. There, you get to do a little bit. Try 18. See if it makes any sense to you. Now you could just plug it into your calculator and you could never do derivative at all. But the whole point of this is to at least do the first derivative. You could do this entire thing on your calculator, but we're trying to do some calculus here. Don't rob yourself of some practice for the test. Well, let me put it another way. If I put this on the test and I don't see the derivative written down, you're not going to get full credit. Let me put it that way. I would expect to see the derivative on this and set it equal to 0. So that kind of gives you an idea how to do this one. We need f of -2, and we're going to use calculator for this one because it's comparing decimals for sure. But we want to find that candidate in the middle. So f prime of x is 3/5 x to the -2/5, which is 3/5 fifth root of x squared. So I just need you to recognize that you have to test 0. That 0 now is a potential candidate for a min or a max. Doesn't have to be. Just because the derivative is undefined there does not guarantee it's a min or max. It's only potential. So now let's compare some decimal answers. -2 raised to the 3/5. -1.516 or 1515. 0 is 0. I don't need a calculator for that. And 3 raised to the 3/5, 1.933. So this time, the interior did not give us a min or a max. Tested candidates, I want to answer it the way they asked. Use a candidate to find the extreme values of the function on the interval and where they occur. Okay, so a max of 1.933 at x equals 3 and a minimum of -1.515 at x equals -2. There we go. Now the difference between 18 and number 20 is 20 does not give an interval. That means anything is open, fair game, any value. So we're going to have to narrow it down. We're going to have to find out where the extreme values could possibly occur. So y prime here is 3x squared minus 2. And let me emphasize that I would give 1 point for this, or AP would possibly, and then this is a possible point also, which seems very trivial. That setting it equal to 0 and writing it down could be worth a point because you're letting AP or you're letting the grader know, oh, I need this to be 0. If you go from this step to saying that x is equal to plus or minus square root of 2/3, you may miss a point for not setting it equal to 0. That seems ridiculous. I know, I get it. But you're telling the grader, I know that the derivative needs to be 0 here. So please don't skip that step. It seems very trivial, but it's not. It could be worth a point. All right, everybody good? I set it equal to 0. I added 2, divided by 3, and took the square root. Everybody good with that? Well, now, let's see, what should we do? For the purposes of this section, I could do this. I could just graph it and go x raised to the 3rd minus 2x plus 4 and graph it. And at negative square root of 2/3, I have a local maximum, and positive square root of 2/3, we have a local minimum. Find the extreme values of the function and where they occur. Local, oh, these are local. Local maximum of blank at x equals negative square root of 2/3, and local minimum of blank at x equals positive square root of 2/3. And I think since we use derivative to find the x values, let's just find the decimal values for this. And there's a couple ways we could do this with the calculator. We could plug it in. So I could do square root of 2/3. It's still kind of a pain. Raised to the third minus 2 times. Oh, thank you. I do that a lot. Minus 2 times square root of 2/3 and plus 4. So 2.911. Which one did I plug in? The positive? Yeah. 2.911. And then if you want to graph it and find those, then you can do second, calculate. I did the minimum. Now I got to find the maximum. And that's over here. So a couple ways to find the decimal values. 5.088. 5.088. And just out of curiosity, calculate, what did I get, a minimum over there? Enter. Did I enter that? Right bound. 2.911. There we go. Yeah. Any questions? This is all about getting the derivative and setting it equal to 0.